Welcome. This is Chapter 2, Section 6 about stresses on an inclined plane. Our goals for today are to perform stress transformation so that we can understand the state of stress in a different coordinate system. This will involve finding the maximum and minimum stresses. You can imagine finding the maximum and minimum stresses are important since we've kind of already established that's how or why things break. It'll also help us find the orientation of the maximum and minimum stresses. So this lecture starts this process. It's going to be continued really over the course of the Chapter 2. That's what Chapter 2 is about. But we've got a couple more lectures about this topic that we're going to go through. The equations that we're going to need from the study guide are equations 2.7 and 2.8. I'm not going to tell you what those details are right now. We'll derive those equations and then we'll start to work with them. So but that's where we're headed. The key for this section is that the magic of stresses and strains, the magic of these things is the way that they change from normal stresses to shear stresses. And the way that they change is based on how we look at them. They are this chameleon kind of feature, and this section is going to look at that. So let's start with a tension stress. So what I mean, and if you remember in the last section, we had this thing that we push on. Oh, my pen's not working. Hold on. All right, my pen's not working, but that's okay. I think I can do it this way. We had this thing that had two eyelets, and it had it was called a dog bone. Boy, that's a really bad. And we took that and then we pulled on it. See, I can't see where my mouse is. We pulled on it that way and we pulled on it that way. Well, okay, let's not do that. Let's jump to this picture. We add a cutting plane. We take this tension, this dog bone that we had, and we pull on it where you can see where we're pulling on it. And then we add a cutting plane that's set by some arbitrary angle, theta, and we're going to want to pay attention to all that, but we're going to move over to a piece of paper because now we're going to have formulas and arrows and a lot of drawing, and I think it's going to work better on paper. So let's transition here a sec. All right, so let's start working on this derivation. We're going to derive these equations. What we're doing is we're starting with this section. So we're going to take this dog bone. It's not quite a dog bone with an eye in it, but you get it. It's got that that force P pulling on it. And if we had a cut there, if that were our cut, you would know what was going on. You would know that there's a force acting on it this way. It's got to be pulling down, and that's going to be equal and opposite. If we looked at one of those forces, we could figure that all out. Well, I'm actually going to cut it now this way. We're going to look at it not all the way to the top. We'll just start here. We'll go down a little bit and we'll cut it like this. So now I've got that force acting up, that's P. And I've got, in order to have this work, right, there has to be this equilibrium force, but I don't want to describe it as, changing colors on you here. I don't want this. That's not what I want. What I want is, I want this force here. This is the normal force to that plane. And maybe I should highlight that's the normal force. And then there's also a shear force. And that's the shear force. I know, and how V works out to shear, I know. But so the last thing that I really ought to do is put a coordinate system on there. And so I'm going to put a coordinate system. Well, we're going to think about this shrinking smaller and smaller. This is going to kind of become a math problem in that way that we're going to, this is happening at a point. Okay. Let's put a coordinate system on there that starts like this. Well, should it start like that? Let me think about that. Let me even pause that, because I think what I really ought to do is have the direction of this force, this, be my x direction. So I drew this wrong. This would be in the negative x, and that's in the y. That's my x, and that's my y. And then I'm going to define theta. I'm going to define theta as this angle from x to n. All right. Let me stop for a drink of coffee. All right. So we've got that defined. Now, let's start working through a free body diagram. I can look at the sum of the forces in the x direction are equal to 0, are equal to, well, in the x direction, I've got P acting in the wrong way. Oh, it's a minus P. It's acting in the negative direction. And that's then plus, that's my normal n. Now, what fraction of that is acting in the x direction? Well, cosine of theta. And I've got my shear force, which is also acting in the minus direction, minus v. And how much of that is acting in that x direction? Well, that would be sine of theta. Right? Okay. Sum of the forces. The problem is I've got two unknowns. Do I have three variables? Well, I do know theta. While I'm saying it's an arbitrary, I do know what theta is. So sum of the forces in the y direction are equal to 0, are equal to, well, in the y direction, P is no longer a factor. Maybe I should have started here. This is going to be n times sine of theta plus, that's kind of, plus v cosine of theta. Let's check that out. As theta goes to 90 degrees, sine goes to 1, and the normal is all in y. So, yep, that would be, okay, I got that. I got that. Okay. So those are my two equations. I can solve, or at least I can start solving this. I know I've got to do trig, I've got to do, but I can substitute around and get that V, the shear force, is equal to minus N times sine of theta over cosine of theta. Now, the reason I chose to do that is because that gave me tangent, and if I did it, I don't want to mess. I'd have to do 1 over tangent, because cotangent, it's trig. It's been too long. Just, no. Equals minus N tangent of theta. And then I can substitute that in up here. So this is, if I start numbering equations, this is 1, 2, this is from 2. And then I'm going to substitute 3 into 1. And I'm going to get 0 is equal to minus P plus N cosine theta minus V times, oh, sorry, not minus V. I'm substituting that in. it's going to be a minus n tangent theta. That's my V. Don't use pen. Don't use pen. And then just don't make mistakes. Don't make mistakes. And then I've got to still have a sine theta. Well, I can get rid of the plus, two negatives are going to make a positive, so we'll get rid of that. But now I've got that mess. So now let's start playing around with that a little bit, and we'll oh, hold on. So we'll keep playing around with this a little bit. Yeah, I rearranged the pages. Sorry about the jump. 0 is equal to minus p plus n cosine theta. I thought I was just going to write this term out a little bit more detail. Plus n, and then tangent is sine theta over cosine theta. But now I've got this extra sine, so I'm just going to say it's sine squared. So 0 is equal to, here's my trick, right? There's always, it always boils down to there's a trick. We want our mathematicians to help us with this. Minus p cosine of theta. So I'm multiplying by cosine over, but multiplying the whole equation by cosine, plus n cosine squared theta plus n sine squared theta. Oh, I know, you're seeing it now. You're seeing it now, and I'm going to keep writing it out in all its painful detail. P cosine theta, did I drop a negative? I did. Plus n times cosine squared theta plus sine squared theta. Yep. That goes away. That's equal to 1. So now something goes across, and I can say that n is equal to, sorry, the p goes away, p cosine theta. I was going to put a negative on there. Good thing I'm not in pen. Oh, wait, I am. If I use that, then I can substitute into what I called equation 2 or equation 3, which was simplified. And I'm going to get that, I'll start with V is equal to minus n sine theta over cosine theta, right? And now my n is equal to p cosine theta. So now this is V is equal to p cosine theta. Actually, I dropped my negative n. That's my p cosine theta. Sine theta over cosine theta. Well, now my cosines cancel. So V is equal to minus p sine theta. There you go. We've transformed our forces so that when we go back and look at our cutting plane, at any cutting plane, it's now my normal force and my shear force are now a function of the load and the angle for any cutting plane. Anywhere I want to put that cutting plane. Any way that I want to look at that problem. Where that becomes important, where that's why we're doing that, is because we want to start looking at things in different coordinate systems because we're the master of our coordinate systems. We choose those things to make our problem easy, and so we may have to convert those things. So we've taken our first step there. All right. Now let's do the same process. But now let's look at stresses. Now let's look at our stresses. All right. Let's redraw that. And you still know that I've got a force P there, right? But I'm going to rewrite that. I'm going to rewrite that as my stress times my area. Now, the way you're thinking about it, we defined that last time as that stress is equal to a force over an area. Well, now my force is P, and so that units, that solves out to be, that force is equal to sigma times A. And similarly, I'm going to have a stress in this direction, right? This has this force N, and that's going to be equal to the stress in that direction times the area in that direction. And I'm going to have one more, right? I'm going to have my shear, which, I'm going to have that shear times that area is equal to my shear force. Now, I may want to think about that differently. In the book, they're going to start this whole discussion because they're trying to transform our stresses. They're going to try to take this and say, you know what? I've got a sigma acting up and I've got a normal and I've got a shear. Well, yeah, that's true. And this normal is equal to P over A. And this is equal to the shear over the area. And this is equal to the, this is equal to the normal force divided by that area that's normal. All right? So I think one of the questions we ought to ask is, what is that area normal, or lowercase? What is the area normal? Well, that's this. That's this area here. So how big is that? Well, remember, this is part of, right, some big prism. Yeah, figure that. Yeah, it's something like that, right? That's part of the big prism. And this is always going to be a unit depth. So what's that area? Well, remember we put this angle here, this cutting plane. Actually, is that the way we want to define it? No. I want to define, this is my x-axis, and here's this angle theta, which is the same as that to that. So there we go. Okay, those are both theta. So if theta is 0, then that angle would just be the angle, that area would just be the area of the top. As that angle increases, I'm going to get that goes actually to infinity. So can you think of a function maybe that goes from 1 to infinity? 1 to 0, so that area goes to infinity? Yeah, I would say that AN is equal to the area divided by cosine of theta. All right. Need a new piece of paper. So if we want to know what our stress is in some arbitrary direction set by some arbitrary cutting plane, right? That stress is going to be equal to N over AN. And that, I gotta put some other paper under here. This desk is not smooth. My pen's not liking it. What's N? What is N? Did we define N in terms of P? Yeah, we gotta go back a couple pages. Wait for it. Back here, N was equal to P cosine theta. P cosine theta. And area of N is equal to A divided by cosine of theta. So this gives us P over A cosine squared theta. That's equation 2.7. That's equation 2.7. Right? I know you're not thinking, here, look, there's equation 2.7. And that first part of it, I can't highlight it on the screen, but it gives you, it's there. P over A cosine squared theta. So we're doing phenomenal. Then the other one we need to figure out is what's my shear? What's my shear? And I'll say it's it's on that N face. That's equal to the shear force over AN, right? Now we had that too. The shear is equal to minus P sine theta, and then I'm going to divide that by AN, which we got that. That's still up here. A over cosine theta. Yeah, this one isn't so nice. This one's not so nice. It's minus P over A sine theta cosine theta. Sorry about the left hand. I was dragging it there, left it on the screen far too long. That's equation 2.8. But you guys can stop the video too once I clear my arm out of the way. And this is where we just have to love our mathematicians. They don't like the cosine squared. They don't like the sine theta, cosine theta. So they're going to change those equations. They're going to rewrite the cosine squared and rewrite those sine theta, cosine theta. And the new equations we're going to get are sigma n is this is the normal stress in the n direction is equal to P over 2A 1 plus cosine of 2 theta. And the other equation is going to be the shear on that n face is equal to minus P over 2A times sine of 2 theta. All right? Now, one thing that is important is looking at theta. First of all, when I pull up this equation sheet, you will see I've got that triad on there. I've got the coordinate system. I want you to recognize how important that is. That got added to the equation sheet later. This is always from a perspective of x, y, n, and t. So now my n is the normal face, and that's the tangential direction. That's normal to the face, and that's the tangential. And that defines x to n defines our direction of the angle. And we're going to run into this right away in our example problem. So we've got to be tracking that. We've got to be aware of that. So one of the things I hope that I will stress to you is once we get an equation, and this is 2.7, this is actually 2.7 and 2.8 also. If I flash those equations back on the screen and slide my stuff up, you'll see that the last part of that equation is what you're seeing on the screen and matches up with what I've got on the paper. I hope what you'll see from me is not only do I just get the equations, not only do I just get an answer, but I want to spend time thinking about it. So when does this equation, let's start with sigma n, when does that have a maximum and when does it have a minimum? So when is this going to be the largest? Well, that's going to be the largest when cosine of 2 theta is equal to 1, because cosine, no matter what's in there, cosine varies from -1 to +1. So when this goes to -1, this whole term goes to 0. That doesn't work good. But when this is when this angle is 0, then cosine is 1, and then this is 2, and then at theta equal to 0, sigma n is equal to P over A. That's as big as it gets. And what that says is, if I go back to my picture, if that angle goes to 0 and these faces are parallel, that's when I'm going to have my largest negative force, my largest normal force, not negative force. When I'll have my largest normal force. That makes sense. At any other angle, it's getting smaller and it's becoming, and it's transitioning into shear. It's starting to look like shear. Okay, here's the winner. Here's the question we really want to see. And that is, where do I get my maximum shear? And you guys know this, you actually did the experiment already. I know, it's only like the second week of school. You've already done the experiment. Shear is equal to minus P over A sine of 2 theta. So when is this going to be the maximum? Well, this will be the maximum when this angle, when 2A, we want sine of 2A, sine of 2 theta to be equal to 1 or -1. That's when that shear force is going to be the maximum. And that's going to take place when, because it's now 2 theta, sine would be the maximum at 90 degrees. And so because it's 2 theta, now it's 45. So at theta equal to 45, sine of 2 theta equals 1. So maybe we want theta equal to 135. Sine of 2 theta is equal to -1. And then I would get a shear force equal to, in this case, it would be minus P over 2A. And in this case, it would be P over 2A. Those are where I'm getting the maximum force. Now, what do these angles look like? Well, I'm going to take my block. I know this face, and so I know that's my x-axis. And one of these faces is going to be when I cut this at an angle. This is going to be 45 degrees, so my cut looks like this. So this would be my N face, and that's my T. All right. Oh, wait, is that, no, that's not right. This is, oh yeah, sorry, I'm sorry, it is right. X, because there's my angle right there, theta. And I'm going from X to N. See, that is a confusing part of this stuff, and you'll get problems wrong because you do X to N wrong and you're missing a sign. The other is going to be at 135 degrees. All right, well, 135 degrees looks like this plus 90. So instead of cutting, let's draw it. Here's this face. Here's my X angle. And so now theta is going to be cut this way. That's 135 degrees. That's my N axis now. Maybe this, well, it would be this. That's my n, and this is my negative n. And well, that looks the same. Well, it kind of is actually. If I draw, hold on while I think about how to draw this best. Yeah, that doesn't entirely. It's not entirely satisfying, but it actually is on the negative n axis. It's pushing in. That n axis is going inward now and not the other way. And that's, we do run into some, oh, sorry, there you go. We do run into some sign issues with shears that are going to show up over and over. But this is now my block. So it's, I cut it at the 45 or I cut it at the minus 45 because I'm dealing with 2 theta. That's what it shows up. It shows up as 90 and 270 degrees. That's where I get these maximums. And so now what you're seeing is, this is where I get the maximum shear. That's where I have the maximum shear. If I want the maximum normal force, it's just where I pull where that angle is 0. And if I want the maximum shear, well, why do I care? Because some materials fail in normal stresses and some materials fail in shear. Now, when have you seen that? When have you seen that? Do you remember doing your concrete lab when you crushed the concrete? Yeah. How does concrete fail? It fails on the 45. Now, does it matter if it fails this way or if it fails that way? No, actually, I could turn over the piece of paper and then they look the other way, right? This one is still, you can see it there. That one's that way, that one's that. And now, so depending on whether I look at it from the front or the back, it still is a 45-degree and it's still oriented that way. And that's a brittle failure. Concrete is a brittle material. And so these equations that we derived, we said, yeah, we're going to push on it. We're going to do this stress. Or we said we'd pull on it, and we're going to calculate this stress. And then it has application. And that brittle materials fail in shear and ductile materials fail in with a normal stress. All right. So there you've got this application of why these equations are interesting, because sometimes we're going to worry about what our maximum normal stress is, and sometimes we're going to worry about our maximum shear stress. So we're going to take this and go a couple more steps forward in the next section. But for right now, we'll jump into an example problem. So with the math behind us, the next thing we're going to do is an example problem. We'll do example 2.6. That'll be in another presentation. And if you're keeping track, we're going to skip sections 2.7 and 2.8. What those sections are going to do is take the principles that we just completed in 2D and apply them to 3D. But if you can do it in 2D, you can do it to 3D. It's just more math, and it's going to slow us up from making other progress. So hope you're having a great day. See ya.